In this video, we will discuss measures of center. A measure of center is a value at the center or middle of a data set. There are different approaches for measuring the center, so we have different definitions for those different approaches. The mean, or arithmetic mean, of a set of data is the measure of center found by adding all of the data values and dividing the total by the number of data values. This is often referred to as the average in low-level math courses. Important properties of the mean: sample means drawn from the same population tend to vary less than other measures of center. The mean of a data set uses every data value, and a disadvantage of the mean is that just one extreme value or outlier can change the value of the mean substantially. A statistic is resistant if the presence of extreme values or outliers does not cause it to change very much, so the mean is not resistant. We use the Greek letter sigma, uppercase sigma, to indicate that data values should be added. The expression sigma x represents the sum of all data values. The symbol n denotes the sample size, which is the number of data values. So the mean is equal to the sum of all data values divided by the number of data values. If the data are a sample from a population, the mean is denoted by x bar. If the data are the entire population, the mean is denoted by mu, the lowercase Greek letter. So for example, find the mean of these data speeds for Verizon smartphones: 38.5, 55.6, 22.4, 14.1, and 23.1, all in megabits per second. The mean is computed by first adding the data values, then dividing by the number of data values. So x bar equals sigma x divided by n, which is equal to 38.5 plus 55.6 plus 22.4 plus 14.1 plus 23.1, all divided by 5, which is 153.7 divided by 5, which is 30.74 Mbps. The mean speed of the mean of the 5 data speeds is 30.74 megabits per second. The median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. Important properties of the median: the median does not change by large amounts when we include just a few extreme values, so the median is a resistant measure of center. And the median does not directly use every data value. For example, if the largest value is changed to a much larger value, the median does not change. The median of a sample is sometimes denoted by x tilde or m or med. There isn't a commonly accepted notation, and there isn't a special symbol for the median of a population. To find the median, first sort the values, arrange them in order, and then follow one of these two procedures. The number of data values is odd, the median is the number located in the exact middle of the sorted list. If the number of data values is even, the median is found by computing the mean of the two middle numbers in the sorted list. Find the median of 38.5, 55.6, 22.4, 14.1, and 23.1. First, sort the data values by arranging them in ascending order: 14.1, 22.4, 23.1, 38.5, and 55.6. Because there are 5 data values, the number of data values is an odd number, so the median is the number located in the exact middle of the sorted list, which is 23.1. Note, this is the same set of values that we used to find the mean previously. The median of 23.1 is different from the mean of 30.74. Find the median of these data speeds: 38.5, 55.6, 22.4, the 14.1, 23.1, and 24.5. Again, we first arrange the values in ascending order. And then because the number of data values is an even number, the median is found by computing the mean of the two middle numbers, which are 23.1 and 24.5. So the median is 23.1 plus 24.5 divided by 2, which is 47.6 divided by 2, which is equal to 23.8. The mode isn't used much with quantitative data, but it's the only measure of center that can be used with qualitative data, consisting of names, labels, or categories only. The mode of a data set is the values that occur with the greatest frequency. Important properties of the mode can be found with qualitative data, and a data set can have no mode or one mode or multiple modes. A data set can have one mode, more than one mode, or no mode. When two data values occur with the same greatest frequency, each one is a mode, and the data is said to be bimodal. When more than two data values occur with the same greatest frequency, each is a mode, and the data set is said to be multimodal. When no data value is repeated, we say there is no mode. Find the mode of these data speeds: 0.2, 0.3, 0.3, 0.3, 0.6, 0.6, 1.2. The mode is 0.3 megabits per second because it is the data speed occurring most often, 3 times. In the previous example, the mode is a single value. Here are other possible circumstances. The data speeds of 0.3, 0.3, 0.6, 4.0, and 4.0 have 2 modes, 0.3 megabits per second and 4.0 megabits per second. Whereas the data speeds of 0.3, 1.1, 2.4, 4.0, and 5.0 have no mode because no value is repeated. The mid-range of a data set is the measure of center that is the value midway between the maximum and minimum values in the original data set. It is found by adding the maximum data value to the minimum data value and then dividing the sum by 2, as in the following formula. Mid-range equals maximum data value plus minimum data value divided by 2. Important properties of the mid-range: because the mid-range uses only the maximum and minimum values, it is very sensitive to those extremes, so the mid-range is not resistant. In practice, the mid-range is rarely used, but it has 3 redeeming features. Mid-range is very easy to compute. The mid-range helps reinforce the very important point that there are several different ways to define the center of a data set, and the value of the mid-range is sometimes used incorrectly for the median, so confusion can be reduced by clearly defining the mid-range along with the median. Find the mid-range of the Verizon data speeds from previous examples: 38.5, 55.6, 22.4, 14.1, and 23.1. The mid-range is found as follows. The mid-range is equal to the maximum data value plus the minimum data value over 2, which in this case is 55.6 plus 14.1 divided by 2, which is 34.85 megabits per second. Round off rules for measures of center. For the mean, median, and mid-range, carry 1 more decimal place than is present in the original set of values. For the mode, leave the value as is without rounding because values of the mode are the same as some of the original data values. When applying any rounding rules, round only the final answer, not intermediate values that occur during calculations. For example, the mean of 2, 3, and 5 is 3.333333 repeating, which is rounded to 3.3, which has 1 more decimal place than the original values of 2, 3, and 5. As another example, the mean of 80.4 and 80.6 is 80.50. Because the mode is 1 or more of the original data values, we do not round values in the mode, we simply use the same original values that are modes. We can always calculate measures of center from a sample of numbers, but we should always think about whether it makes sense to do that. We previously saw that it makes no sense to do numerical calculations with data at the nominal level of measurement because those data consist of names, labels, or categories. We should also think about the sampling method used to collect the data. If the sampling method is not sound, the statistics we obtain may be very misleading. Below we see some situations in which the mean and median are not meaningful statistics. Zip codes are numbers but do not measure anything. The numbers are just labels for geographic locations. Ranks of selected national universities reflect an ordering but do not measure or count anything. Numbers on the jerseys of Seattle Seahawks players are just substitutes for names. Top 5 and top 10 lists may include data that are not at all representative of the larger population. This formula is the same calculating the mean from a frequency distribution. This formula is the same calculation that we used for the mean before, but it incorporates a new approach. When working with data summarized in a frequency distribution, we make calculations possible by pretending that all sample values in each case are equal to the sample midpoint. To find the mean from a frequency distribution, First, multiply each frequency and class midpoint, then add all of the products, sigma of f times x, and then divide by the sum of the frequencies, sigma of f. So x bar equals sigma f times x over sigma x. I'm sorry, that should be over sigma f. The first two columns of this table are the same as the frequency distribution of McDonald's lunch data in chapter 2. Use the frequency distribution in the first two columns to find the mean. So we've got the frequencies 11, 24, 10, 3, and 2. And the class midpoints 99.4, 149.5, 199.4, 249.5, and 299.5. When we add all of those together, we get 1,094.5, 3,588.0, 1,995, 748.5, and 599. To get our mean, we take x bar equals the sum of f times x divided by the sum of f, which is 8,025, the sum of all of those f times x's, divided by 50, which is 160.5. When different x values are assigned different weights w, we can compute a weighted mean. Weighted mean x bar equals the sum of w times x over the sum of w. This formula tells us to first multiply each weight w by the corresponding value x, then to add the products, and finally to divide that total by the sum of the weights, sigma w. In her first semester of college, a student of the author of our textbook took 5 courses. Her final grades, along with the number of credits for each course, were A, 3 credits, A, 4 credits, B, 3 credits, C, 3 credits, and F, 1 credit. The grading system assigns quality points to letter grades as follows. A equals 4, B equals 3, C equals 2, D equals 1, F equals 0. Compute her grade point average. Use the credit numbers as weights and replace the letter grades with their quality point values. So x bar equals the sum of w times x over the sum of w. So that's 3 times 4 plus 4 times 4 plus 3 times 3 plus 3 times 2 plus 1 times 0 divided by 3 plus 4 plus 3 plus 3 plus 1, which is 43 over 14, which is 3.07.